Hello everyone, this is Nandini and my teammate is Aravind. Today I'm going to present the topics on Rubik's Cube Solver with Mode Track feature. Project objective. The objective of a project is to develop an artificial intelligence model capable of solving 4x4 Rubik's Cube using reinforcement learning. Solving such a cube manually is a complex task due to massive number of possible configurations. Instead of hard coding solutions or using brute force, our goal is to enable an RA agent to learn solving strategies purely through interactive or one with a stimulator cube environment. By rewarding successful moves and penalizing incorrect ones, the agent gradually learns an optimal path to the solved state. Our implementation uses state-of-the-art deep R algorithms and offers a step towards intelligent self-learning systems that can adapt to complex puzzles. Now let's go to the approach, the introductions. The Rubik's Cube is a symbolized puzzle of logical thinking, spatial awareness, and memory. While many people solve it using memorized algorithms, our approach focuses on teaching a computer to solve it autonomously without human derived heuristics. The 4x4 variant significantly increases complexity over the standard 3x3 version. In this project, we aim to use reinforcement learning to let an agent learn how to solve it purely through experience. This problem provides an excellent test base for RL because it has well-defined environment, clear rules, and measurable success conditions. And it comes to the methodology. Our approach begins by designing a simulation environment using OpenAI, which allows the agent to interact with virtual Rubik's cube. The environment represents the cube current state and allows specific actions, valid moves such as face rotations. The RL agent observes the cube state and selects an action, receiving feedback in the form of reward. A positive reward is given for moves that bring the cube closer to the solved state, and a large reward is granted once the cube is fully solved. Negative reward discourage moves that worsen the state or repeated actions. The training process uses deep network or proximal policy optimization, which are neural networks based techniques that enable the agent to predict the best action from the given states. Over thousands of iterations, the agent refines its policy to maximize rewards, essentially teaching itself to solve the cube more efficiently. System overview. System flow overview. The system follows a structured flow that mimics a logical problem solving pipeline. It starts when a user inputs a scramble cube. This is the diagram for the flow graph, either manually or through code. The environment setup phases prepares the cube and initializes the RL environment using OpenAI GYM. Next, the RL agent processes the current state of the cube and determines the best mode to make. The decision making is based on what the agent has learned from the past experiences. Once the agent generates a sequence of moves, the solver applies them one by one. Simultaneously, the mode tracker logs each action, which is essential for performance evaluation, debugging, and visualizing how efficiently the agent solves the cubes. This end-to-end flow ensures that the process is traceable and modular. Now let's go for the implementation architecture and the reinforcement learning process. At the core of the project is the RL loop. The agent begins with no knowledge about how to solve the cube and acts randomly. After each move, the environment responds with a new cube configuration and a numerical reward that tells the agent how beneficially the move was. These interactions are stored in the agent's memory. Over time, the agent trains a neural network to predict the best move for the given. This continuous cycle of the action, feedbacks, and policy updates allows to agent to gradually learn a strategy that leads to the solved state faster. As training progresses, the agent transitions from random modes to intelligent goal directed behavior. This mimics how humans learn by trying, failing, and adjusting their approach based on the outcomes. This is what the reinforcement learning process shows us here. And when it comes to the deliverables, we'll provide several deliverables as part of the project. This includes the full Python code base used to create the train the RL agent, as well as the train model itself. We'll also deliver documentation detailing the project architecture, methodology, and results. A comprehensive, uh, a complete presentation is given in this, which is included like summarizing and presenting the work.
Hi, I am Aravind. I am explaining the code of Rubik's Cube solver with the Moo tracker. I am explaining the two files. Here I am using two files, puzzle.py and Moo tracker agent.py. First of all, I am explaining the puzzle.py because I am using this file in the Moo tracker agent.py. In present, import random and import copy. What is the meaning of import random and import copy is used for the generating random numbers, particularly for shuffling the cube. copy means used to create deep copies of the object. And coming to the colors, I am using white, yellow, red, orange, blue, green. These are the colors I am using in the cube. 6 means the total number of sides of the cube. And state means class representing of the state of the Rubik's cube. int is the constructor initializes the cube size and colors. If a configuration C provided, it uses that, otherwise it initializes each side of the uniform color. And also coming to the this one is the this part indicates the cube initialization. Initialize the each side of the cube corresponding color using the repeat as a list. And this one is a state representation of the cube. And the sides list of the sides of the cube. D indicates the dictionary mapping side names to the respective list. And this one is a copy method. This part is a copy method. Copy method is to represent a deep copy of the current state of the cube. And this one is a string presentation, provides a string representation of the cube's current state. And this one is the hash method. This one is used returns a cube's string representation, allowing it to be used as a key in dictionaries. And this one is a goal state. Goal state check means a check if all the sides of the cube in a single color, indicating the cube is solved. And this one is a move method. This one is a move method. Move method is execute a rotation based on the specified action and updates the sides of the cube. This one is a turn method. This one is each method rotates the corresponding side of the cube using rotate 2D function. These are the utilities functions. And the utility function mainly is this one indicates the first line, the first two lines indication that creates a 2D list filled with the specified value. And these two line indicates rotates 2D matrix of 90-degree clockwise. This one is a state action. And this one indicates returns a new state after applying the specified action to be the current state. This one indicates shuffling the cube by applying a random action multiple times. This one indicates that creates a new shuffle state of the cube n random moves. And this one indicates counts how many sides of the cube are completely solved. That means all cells are the same color. And this one indicates counts how many pieces are correctly placed on their respective sides based on the middle pieces colors. This all indicates. And this one is puzzle.py. I am going to the move tracker agent.py. Coming to the point, move tracker agent.py, import random time from puzzle. That means random means from generating random numbers, and time indicates for adding delays during payback. And puzzle indicates puzzle. This one indicates import necessary functions and classes for managing Rubik's cube state. And agent class. Agent class is a Q learning method. Q learning agent that will learn to solve the Rubik's cube. int indicates initialize the agent's attributes including visited. This one indicates visited. Tracks visited states. This one is the visit count. That means is counts visits to states. QV is a variable. Stores Q values for the action pairs. This one. And start state is equal to this one is the start state. This one indicates initialize the cube state, either a given state or a shuffle one. This one is the move tracker. That means requires the sequence of the moves made by the agent. This one is the move starts. Move starts means counts how many times each action is taken. This one is the indication of the initialize the Q values for action pace based on the default state. Rewards are set for correct actions, penalties for incorrect ones. This one all indicates the Q learning method. This one starting from this one to and here until here is the Q learning agent Q learning method. This one explains the runs of the specified number of episodes. For each episode, it explores action for using an explain greedy policy. That means choosing the best known action for our random action. Updates Q values based on the received rewards and the maximum future reward. Coming to the this paragraph, this lines indication the package playback of the learner policy. Execute the learner policy by moving through the cube's states until the goal state is reached, printing the current state at each step. Coming to the this one is the this indicates move sequence management. This line indicates the show move sequence, displays the sequence of the moves made by the agent. This one indicates saves the moves sequence to a test file. This one indicates reward function. Calculate the reward for taking a specific action in a given state. Rewards the for reaching the goal state. Penalize the for each move and rewards for progress towards solving the cube. Main script. Initialize the agent register patterns. Trains the agent over a few episodes. Playback the learn policy and saves the move sequence along the statistics. I'm using reinforcement learning that learns to solve a 4x4 Rubik's cube with the move tracker. Using a Q learning, it tracks actions, updates in knowledge based on the rewards, and payback its learner strategy. It is evaluated based on the efficiency and it moves and the time taken to reach the goal and state. Coming to the output, I am explaining the output now. I am running the code. This line indicates this all lines indicates one second. This all lines in display is the current state of the 3D puzzle. That means each face front, back, left, right, top, bottom is shown as a 3x3 grid and identical colors indicating solved state. If you observe in the episode 0, goal state is during reached. That means this indicates the training episode 0 was successful and the agent is the reached goal. Yeah. A goal reached. Means this indicating episode 0 was successful and agent reached the goal. And also if you observe in the 2 times, that means solved the puzzle 2 times during the training, possibly due to the restarting or replaying the episode. For example, this one indication is the policy payback. This means the agent is now replaying the steps it learned to solve the cube. The final state confirmed and it is successfully reached the goal again. And coming to the move statics. Move statics indication. This one is the move statics. Move static is the front 0 and back 0 and left 0 and top 0 and bottom 0. This indicates the dictionary indicates how many times each face was rotated during the payback. All values being 0, that means that either the cube already in solid state before payback or the move statics one properly. These are the explaining of the cube. This one, and I am explaining the remaining part of the PPT. Until delivery is my friend explaining the parts, and I am continuing the remaining part of the elevation criteria. In the efficiency and accuracy of the solving, it indicates the how quickly and correctly the Rubik's cube is solved, and what is the meaning of what is the use of the move log quality is that the quality, the clarity and useful and recording steps are moves. Documentation quality is this one is the documentation quality. How well the project is explained in a written form. This one is a completion time. How fast the overall task is completed. This one indicates the user feedback, opinions or satisfaction levels from users who interacted with the system. Coming to the reference, I am taking the reference a publication on reinforcement learning, especially its theory and application to solving the Rubik's cube, which likely provided fundamental knowledge for the project. And thanks you for giving this opportunity.